Okay, right now, and I'm sharing the whiteboard. Right now, the algorithm is such that we have this tiling graph. And in this tiling graph, we are wanting to infer that this is a thing. And what I just realized something. Oh, maybe that's the problem I just found. So in this specific graph, if we start at the red vertex over here, what about this vertex here? Is it structurally identical? I think it's structurally identical, which is like a problem thing, right?
You mean the one, I mean, immediately to the left of it?
Yeah, this blue vertex is, well, it is the same, but it depends what assumptions we make. Assumptions, or depending on how we compute the equality.
Yeah.
Because any vertex, if we do a BFS search, the graph looks exactly the same for any vertex. If we do BFS of depth 5, the sort of graph is the same that we get in terms of just the connectivity of the vertices and edges. Does that make sense? Why this is the case?
This seems right. Like if this was sort of filled out, right? Like if we, like every vertex has 3 edges.
If it's filled out?
Like, I mean, is this our entire graph here right now, or is this just a section of the overall graph, and this is just sort of pointing out what structure the graph has?
Let's assume it's infinitely tiling.
Yeah, like in that case, every vertex has 3 edges.
Yes, and if we expand it further, it will still tile, right? This is like, sure, this has 3 edges. This has 3 edges. This has also 3 edges. This is also 3 edges. So actually, wait, is that really like that? I think like I'm confused. I think there is something we're missing. I guess what we're missing is like structural equality. Like I could generate this graph over here for BFS1, and then I get this. And then I can generate it for this, which is this, which is structurally sort of the same.
Yeah.
But actually, if we were to compare these two graphs and to compare the vertices in the graphs, if that is a thing we could do, it would not work. Like, what I mean is, well, I guess, let's see, the problem is we don't really have, like, do we have, okay, I'm a bit confused. Like, the thing that we actually want is that these vertices, like we want to sort of know that we have sort of reached these red vertices, right? We want to be like, these red vertices, they are all the same.
Yeah,
And
I
we
think
don't
that's
want...
Yeah, I think that's like an assumption that we don't need to make. Like, this is not the necessary reference point. Like, okay, it works for the red ones, but it also works for all the blue ones. And
No, like the problem is that the current algorithm is like trying to search for a bunch of vertices which have the same structure. But what does this mean? Like, it doesn't work in this graph if this blue vertex has the same structure as the red one. But in the sense that, like, we want to... Or is this even a problem? Like, the thing is, we want to find the repeating structure, the exact repeating piece, sort of. And it feels like the blue one is just messing things up.
I sort of get your intuition there, but I don't think it's a problem. That just means that, I mean, so in some sense, it means the graph is more regular than we thought. So we don't, like, we see the repeating structure not only from the reference point of the red vertices, but also from the reference point of the blue ones. But it's the same kind of repeating structure, no matter which reference point you get to. Like, it could be that there's another kind of repeating structure around the blue one that is unlike the repeating structure that you have around the red one, and then it would be an issue, I guess. But then, of course, you also would say, okay, if I sort of sample these differently, then I see 2 different structures, so I don't have a tiling thing, and I need to sort of expand. But because it's the same structure, it doesn't matter. Like, that just means that the overall property of the graph is like it's even more structured than just allowing you the red ones as reference points.
Okay, what if we have this very similar graph, but now the vertices are connected such that, well, it's gonna draw it like this. Aha, now actually we don't have it. Now the other vertices have 2 edges or 4.
Yeah.
So now this would not be the same. Actually the BFS would just go here. The BFS would actually detect that we have equality with all of these if we just expand for one step. Which is definitely not... Wait, is it right? No, it's wrong. If we are starting over here, then the BFS would be all these red colored nodes, but actually there's a bunch of nodes missing.
Yes, would be 6.
And now the structure of this is though actually... Wait, I'm now confused. Well, yes, the structure of this is the same as of this. Makes sense.
Yeah.
Structure of this is the same as this or this actually. They're both the same. I think for this it would be different again. Okay, so
Yeah.
BFS for this, we can just draw the graph. So it would be this, and then we get 2 here. And then, actually, yeah, it would be like this, and then here would get this.
You're missing 1.
Yeah, actually I'm missing more than 1. Am I?
Like for the central one, you still want to have an edge to the right.
Right, and not 1 to the left. That doesn't make any sense. Yes, so yes, then it's 3, exactly. And for the top ones also 3. So, but these edges wouldn't be in the BFS.
Wait, you're confusing me. Like each one of the like the big red one has 6 edges, right? 2 local ones to its own like little cluster, and 4 ones to the adjacent clusters.
Okay, yes, I guess I just drew it all. Well, the confusing thing is that here I'm drawing the edges in, and here I'm not. Like, obviously, yes, there's an edge over like this, and an edge like this.
Yeah. I'm just talking about the central red one having 6 edges, and like in the top version it has 6 edges, and it doesn't in your bottom version.
Yes, 1, 2, 3, 4, 5, 6. Now it has 6.
Yeah.
Yes, they have always 4. I mean, obviously, that is the way to think about it. They have 4 because it's a lattice.
Yeah.
And 4 except these 2, which are not, are like sort of internal.
Yeah.
So I guess we don't want to draw it like this, but like this. And then also like this. So that means here we have 1, 2, 3, 4, 5. So we get this for the red vertex. For this blue vertex.
Wait, why is it 5?
5? I mean 6, but 5 that are...
Okay, good. But the original red one in this sort of drawing down there, this one still has 5 total edges.
All right, yeah, that's wrong.
Like we still need one to sort of go, like, I don't know, underneath the local ones or something.
Yeah, the one to the right's missing.
Yes, that's the one I was... Okay, now it's all.
Actually, we need to be able to compare the vertices, otherwise how do we even do a BFS search? It just kind of doesn't work. Like, here I'm expanding to this vertex, but then also I don't want to add another one. This is the same. I need to know that they go here, sort of, right? How do you do that? Like, you need to somehow be able to compare vertices. Is that just a thing you can do?
Yeah, I also wonder about that. Like, that's an important thing. I think this is why I
ask GPT. In graph theory, what functions are we usually assuming that we have for the vertices? Is it always the case that we can compare two vertices for equality? And that we can potentially even compare edges for equality? It seems that really common graph algorithms like breadth-first search would not work if we couldn't compare quality of vertices, because we wouldn't know when we want to terminate the search. I guess it would still work for just iterating all vertices, but for example, we couldn't sort of generate a subgraph with the BFS because we wouldn't know if we need to add a new vertex and connect it or if we need to add an edge to an existing vertex.
Yeah, if you can do this, I don't know, like marking the vertex you visited.
Well, you can compare two vertices. So if you are visiting a new vertex, you can check if it is equal to one you already visited.
Yeah, okay. Yeah, in that case, you should be able to do it. It's just a parallelization issue. Parallelization.
I have no idea what you mean with parallelization.
Well, if you have like if I want to do a breadth first search for multiple steps, I could say, okay, like I'm doing sort of one step now, and then I'm like recursively doing the same thing for each of the new locations, for each of the new vertices that I reached in my first step, right? So I'm basically always spawning a new breadth first search of one from my from my current next one. And if I want to be efficient about it, I can run all of these things that I spawn in parallel. But while they're running in parallel, I can't compare the marked ones.
Well, I mean, depends on your algorithm. If you have an algorithm, actually, that's the thing I was just thinking about yesterday, where we can generate graphs with doing a sort of breadth first search procedure as a general method to compress graphs. And then it makes sense to parallelize it. But it makes sense to parallelize it, or like, I guess it depends how expensive is I'm expanding into the next vertex, sort of. I'm adding the vertices for the breadth first search here. And then, yes, because there are two steps, right? There's like, what are the vertices on some vertex I'm expanding? And then for all of the vertices I have expanded, how do they need to connect to for the graph I already have?
Yeah.
And if you were just to the search, you would do sort of, you still actually need to actually you need to do exactly the same thing because you need to check did I already visited the vertex that is behind this edge. So like you need to have the right edge, otherwise you would generate the vertex, but then you're like, yes, just continue, but like you might have already been there.
Yeah.
And then it would be exponential, then it would be very terrible performance. So you can parallelize these two steps. Like you can do all of the vertex expansion for every vertex. It doesn't depend on the other vertex expansions. Only the edge connections depend on that.
Yeah, that makes sense.
So if we expand this other vertex, so like, okay, so now we know we can compare things for equality. Okay, there's not enough space here.
By the way, I need to go in about 20 minutes because I want to prepare for the that I have after.
Okay. So if we start at that vertex, then, okay, also if we do breadth first search, probably good if we just say the step. So this would be the graph after two steps. Yes, okay, now I can just super easily read it. But now we just get sort of, now we get just this, right? Because we had this vertex and do this, like what you're saying, the breadth one search. And here it would be like, this would be 1, 1, okay, but actually all 1. So definitely, the problem here is actually that is not really 1. It is actually 2. If like this is exactly the same as if we drew this, right? Like breadth first search is not like add some edges and ignore the vertices. It's just I sort of didn't draw the vertices. Or we could think of generating that weird graph, but that's not what you kind of would do, I guess.
Yeah.
So this is the actual graph we generated. So if you look at just the first step, then it's just like we have 4 vertices connected to us. Here, we definitely don't have that, so it's already different. You don't even need to go to step 2. It's different for step 1.
Yep.
If we start at this vertex, it's exactly the same. If we start at this vertex, wait, but now this original problem, because we have graph equality, is kind of solved, I think. Because we can say, no, never mind, no, we can't do anything. Well, the thing we can do is actually, like, okay, now that we have equality, which I think was the main confusing thing that we were confused about. I think with equality you can resolve this somehow and say this is not what we want. Okay, but first let's do this example. okay, it's actually the same as this one. For the first, well, actually this is just wrong what I drew here, because I said step 2, but actually we have in step 2 also these things.
Yes. One more.
Yes, this one. Wait, really? And even more. This is just still missing one, right? Is it?
No,
no,
that's
wait.
correct.
No.
It's sort of 2 local
Yes.
ones and 4 like lattice ones, basically.
Yes. Okay, so this is different from this. They are all different. For BFS,
Well,
BFS of size 2.
yeah, but the sort of bottom right version has an equivalent if you just start from bottom vertex. Like if you start with the 2.
Yeah, if I start here, it's like yes, it's right. Which is actually, I guess, still a problem then, is it?
I didn't think it was a problem to begin with, but it's hard to explain. Like, I guess I don't really know how to formalize it. It's just like how much overlay or like overlap is there in terms of structures that you can use to sort of tile things.
Yes, I think that's right. It somehow is not a problem in this case. I think because we could, well, the thing about this is that, so we're doing this of size 2, and this is a very special case actually, because there is sort of this vertex which is like the bottleneck for the inner structure of the lattice nodes. Because if I'm on any of these sort of inner structure nodes, I need to go through that red vertex to go to any other lattice vertex.
Yeah, I mean, we had this to a lesser extent in the original lattice thing as well that you were talking about, where like in the top left version here right now, like they connect very smoothly. Like every vertex has 3 edges, and so from every vertex there are like 2 local connections and 1 lattice connection, and so the 4 lattice connections are distributed across the 4 vertices.
Yeah.
But you can like basically distribute these 4 lattice connections arbitrarily among the 4 local nodes.
Yeah, exactly.
Yeah.
We want to say,
and in each case you do have the lattice, and in each case you do have the repeating structure.
Yes, which could also be more than 4 nodes, and it could be arbitrarily connected to the lattice connections. And
yeah.
But I mean, the algorithm should also, I guess, work with any lattice size. So we don't know that there are 4 lattice connections, but I think I solved that problem. I think I know I think probably you can actually detect the correct dimensionality. I have some algorithm for it. I think it's slightly wrong, but I think you can do something where you're like, aha, this thing happened, therefore the dimensionality of the lattice is n, or 2, or 3. Okay, but let's think about, so we wanted to do this because we want to basically find these red vertices, right? We want to say, given that I start somewhere in the graph, when did I reach sort of in the other structure, like in another lattice node, when, like what, well, so we want to do something like this. So like we have a replacement graph, which is this 4 thingy thing. And now I want to say, like, I select any vertex in the graph, and then we selected some vertex somewhere in the replacement graph, right? And now we want to make it such that, like, find in adjacent replacement graphs in the lattice the vertex that is sort of the same. Right? Like imagine we labeled in the replacement graph, we labeled all of the vertices. Then we want to say, in all of the adjacent replacement graphs, find the thing that's labeled the same. But we can't see the labels.
Yeah. I mean, this is like almost like a label tiling thing. I mean, you can say, well, now my overall graph is tiled with structures that are labeled like this. Or that can be labeled like this.
I think then if you want to frame it like this would be a problem that these 2 are the same, because you cannot find, like, I think this might be too strong of a thing. I think
Yeah.
because we want to actually just infer what's the replacement graph. And well, well, what we want to infer is the replacement graph, the dimensionality of the lattice. Okay, so replacement graph, dimensionality of the lattice. So I guess in this case we could for now assume it's just the 2D lattice. And like the sort of, I guess now I could say the graph construction function. So that's kind of, I guess, slightly not what I was thinking about yesterday. Like I mean the function which takes this replacement graph and lattice replacement graph connectivity is what we need. Like I have the edges that are this like vertex in the lattice, like a 2D lattice has 4 incoming edges, and I want to say, okay, the replacement graph, how do these edges connect? Like for example, I could say that this edge goes over here, and this edge goes over here, and this edge goes over here, this edge goes over here, something like that.
Yeah.
I need that also. And then if we invert all of that, then we just have a generating model of the lattice, meaning we can just, even if the lattice is infinite, this just describes the lattice. Well, not the lattice, but this this specific data structure of a lattice which is regularly substituted with the graph.
Yep.
And the first step is to find structurally similar like if I know that this vertex is sort of the same in these adjacent ones, that seems really useful. And I think this is sort of, I mean, is this a problem? I'm still confused about it.
I mean, if it is a problem, then it's the same problem as in the top left.
No, I think this problem could be solved, I think. So, okay, very quickly, I think this problem I would solve it by, like what we can do, I think, is we can compare vertices, right? Or we can, so the thing is that if we were to look at this graph here again, well, okay, that's a bit, there's no space. So okay, I think what we need to do is we need to color the vertices now, make it easier. So we have one black vertex, and this vertex, so this is basically now the labels.
Mm-hmm.
And well, if you think of the BFS for this thing, you would get stuff like for example, if you start with the orange, then we would get orange, black, red, and then again orange. Wait, no, not orange.
Well, you get purple to the left.
Yes, exactly. Okay, and what we can do now is, and now imagine we expanded from the black one. So then we would do black, red over here, purple would be over here.
Wait, no.
Wait, what?
Yes, here. Because the red, yeah.
And then orange over here. And now,
well,
it's different. Is it? Wait, I'm confused.
Like the red, the black one is opposite.
I understand. I was confused. This is not. Sort of we need to do that, but we need to. Okay, we can compare vertices, right? So what I actually want to do is sort of we want to say this is vertex 1, and then we say 1, and then we are like, look, this contains vertex 1 also. Like these are two BFS things, but this vertex is contained in this one. Like they are equal right now, but they contain sort of the same vertex. And it feels like what we can do here, if we do this kind of thing, is we could sort of check if we have the largest graph which doesn't contain the duplicate vertices or something. Like we're trying to grow the graph as large because because there is a larger graph that we can do, right? Here we pick this vertex and this vertex, but actually if we picked sort of if we were to pick sort of the 1 and the 5, then they wouldn't overlap. Then I can draw this boundary, which is 4 vertices, and I can draw this boundary, which is also 4 vertices, and no graph contains a vertex from the other graph. But if I draw it like this, like if I were to select 3, then it would be then it would contain less vertices. So we could check, we could increase sort of the BFS and see that we get like graphs that sort of don't overlap as much with this, I think. We could be like, yes, try also this vertex. And it's like, oh, this vertex and this, they are better with this pair of vertices, but you have to have more than 2 usually. But like these pairs, this is a better pair than this pair, because like now the graphs are larger.
Yeah.
I think something like that might...
Yeah, I still think like the original insight was sort of, you look for the largest thing that appears like in both, or in all patches, in my version, but like 2 patches suffice, so that's sort of your original approach. And you sort of check what is the largest repeating structure in both, and you sort of do this until like you make this larger until like it doesn't match anymore, and then you sort of got your candidate. And here we are just saying, okay, we don't want these structures to overlap, so we need to label them somehow.
Well, we're not really labeling them. I guess I labeled them to make it easy, but the only thing we actually do is just check if a graph of one vertex is in a graph of another vertex, which is it doesn't require labels to do. Well, I guess I was still a bit confused about how you would do the equality relation, but having unique labels on your vertices, is this, or maybe this is actually just, we always have that easily. Maybe the thing in graph theory is that the edge labels make graph isomorphism easier and the vertex labels don't. I'm not quite sure. If it seems like it might be possible that the equality relation is a weaker assumption than I have labels on all of my vertices. Also, this definitely doesn't work still, because this would just grow infinitely. But something like this might be a good thing to use. Okay, now I think we're out of time. I don't
actually think it's a problem, but
now this is a problem.
On how you compute equality.
The problem here is at what point do you stop? Because of course I could sort of go into this lattice over here and be like, aha, I select this vertex over here, right? This is sort of, it is actually exactly structurally the same vertex as this, and it has the property that is even larger than this, because now it can go up until like well, here, I guess. And this can expand one further. But now it wouldn't tile anymore. Wait, what? That doesn't make any sense.
Wait, if you select multiple tiles instead of one tile, then those multiple tiles still like end up tiling your thing as an object, right? Yeah.
What do you mean tiles as an object?
Sorry, what I mean is rather than like if we look at the top left thing here, if we just see these 4 things, like these 4 little clusters connected, we could say, well, these 4 together, like this is one tile. And that would
cluster?
sort of work. Yeah, this thing is sort of one tile, and like that would sort of, that would satisfy our tile check.
So the problem is like, if this is infinitely large, why do you say this 4 thing is the tile? Or the 100 repetitions?
Yeah. I mean, there's this thing where you can either say, hey, I have so many valid tiles because any grouping of previous tiles makes a new tile that also works, at least for my infinite graph. So yeah, okay, yeah. I guess I'm a little bit confused now as well. Let's think about that more next time, because so that makes me think, wait, so I do want to have this like smallest valid tile, but and then the smallest valid tile, but it doesn't, it has to be a vertex including edges. So if it's like a vertex with 3 edges, if that was my smallest tile, like if every vertex has 3 edges, then that's fine. But can I sort of form different structures, like different graphs, even if all vertices have 3 edges? Probably. And then, that's the sort of question. Like you can't say, either the smallest tile or like the largest thing.
Well, so this is definitely... Okay, okay. It definitely is possible to say this is not that this graph is not described by every vertex has 3 edges, right? Because if I draw that graph, every vertex has 3 edges is this graph. Okay, I drew it like this. Actually, it would be much better to draw it as a tree, but this is a sort of a tree that grows very fast. And you get like this thing. Yes, okay. I
Now
guess
you
you
have
can
4
draw
edges, but I
a
get what
tree
you're
as a
saying.
circle. 4 edges?
Yeah, only the most inner one has 3. The other ones have 4 right now because they have an incoming and 3 outgoing. But I get what you're saying.
Okay, then it would be different. Okay, yes. Then it would be 3, 2.
Yeah, it's always 2.
Mm-hmm.
So.
Yeah, but this is not this graph. This is not the lattice graph.
Is it not?
No, because
it isn't. Yeah, no, you can't do it like this.
The problem is that some vertices now are not the same. Some vertices are merged. Basically, we can generate this graph by in this graph merging some vertices.
Yeah.
Because like the thing is, if I can go over here and then I get something, but I can also go over here and get the same thing, and so they must be the same. It's not, and here's always different.
Yeah, it's true. It's true. Like if you want to get from one branch to another branch, it's like you might have to go to the root to get there, the uppermost one, and like. But
this property is probably this. You could use that to detect. Like, not sure it's necessary. That's basically we're not doing that so far. So we're just like what's like some more localized structure. But you could definitely check that this, or like, yeah, maybe this is even better. You're not sure, but you could do something like pick some arbitrary vertex, then like pick one edge, then go very far from this one edge, and then pick another edge and see if when you reach the like first edge, and that kind of thing.
Yeah.
Or like something more like what vertices can I reach from this edge in how many steps? What vertices can I reach with this edge in how many steps? And if you're on a lattice, then if you're on a yes, then it would always be that there are multiple ways to reach the thing. And I think you could maybe analyze the structure of like how you're reaching these things.
Yeah. Okay. So yeah, I still need to do the testing step in that case. Like I can still say, okay, I have like this is my tiling candidate, my smallest tiling candidate, and now I'm checking.
But yes, you somehow still do some computations, I guess. I'm not even sure that you need to check sort of this tiling. That's this tile thing. Maybe that would be implied. I'm not sure. But that would certainly like, that would be true in a lattice and not in other graphs that you had this kind of behavior of you are able to reach. Yeah, this is like a general strategy for analyzing this, I think. You have like, you just go on one edge and then you delete the edge. And now you do BFS from that edge and you think about what you reach or something like that. And then you delete that edge and then you look what you reach.
Yeah. Mm-hmm. I need to wrap up.
Yes.
But yeah, I think, I'm going to think about this some more.
You want to quickly do reflection?
Seemed good.
And do it.
Like I think we were both a bit tired today, and I think I understand. Like I think I missed like a problem about this tiling algorithm, and now I understand it better. So
I think there are a bunch of problems.
Yeah. But like there's sort of one deeper problem that I'm now like appreciating more, where I'm like, oh yeah, okay, it's like there was like a low resolution algorithm in my mind that basically said, well, this seems like maybe not trivial, but like this definitely seems like easily solvable. And I'm like, oh wait, no, not necessarily. I don't actually find it easy to like quickly generate a solution for this. So that's a good thing to check.
Yeah, I think one thing I did wrong is I didn't review the notes from our last meeting, and so I didn't consider as a possible topic to continue the thing that we did last week. But once you brought it up, it was pretty obvious that would be the best thing from my perspective.
Mm-hmm.
So I guess a general thing is like, before a meeting, always review the notes from last meeting. I mean, it's, yes, I guess I'm never doing that. Seems like a good thing to do. Before a meeting, review the notes from the previous meeting. or at least to the extent that you remember roughly what was done at all.
Yeah, like mostly to see whether it would make sense to continue, or like as an inspiration for where to go in this meetup. It's like a good thing to come, like you have like your current mind state on that particular day, and you want to like somewhat synthesize, or like, I don't know, combine that with what past meetings were about to generate like good ideas.
I think the last meeting was really good, and we did think about lots of good things. And the problem was just that I didn't remember it. That's a problem. That's like I'm not saying force yourself to do the thing that you did last time. I'm just saying, because it was 1 week, I guess, I didn't even remember it.
Yeah.
I actually completely forgot that we were working on this algorithm. I thought, but I remember that I was working on this algorithm, but I actually forgot that we were working on it and how much progress we made.
Yeah. Okay. Like seems like a good enough reason to do like a quick review, just as a general practice.
Yeah.
All right. Yeah. But I thought it was a good meeting today as well. My understanding has improved, and talk to you in a week.
Okay.